Newton's laws of motion are among the easiest topic to learn, but often the trickiest to apply. This problem represents one such application. Without further ado, let's dive into it. We have a man of mass 60 kg standing on a light weighing machine inside a box of mass 30 kg as shown. The box is hanging from a pulley through a light rope and the other end of the rope is held by the man himself. Now there are two cases that we need to consider. If the man is able to keep the system at rest, then what is the reading shown by the weighing machine? And the second is, with what force should he pull the rope for the weighing machine to show his actual weight? Now let's begin by understanding the forces in the system. Clearly there is a force of gravity that's acting downwards on both the man and the box. There is also this tension T in the rope. Then there is this normal reaction, the force exerted by the weighing machine on the man as well as its reaction, the force exerted by the man on this weighing machine. Now just remember, according to Newton's third law, if the man is pulling the rope with the force F, then it is equal and opposite to the tension in the rope that's pulling the man. Now similarly, the force exerted by the weighing machine on the man, N, is equal and opposite to the force exerted by the man on the weighing machine. Now let's draw the free body diagram of the man, and in this diagram we only show the forces that are exerted on the man, not by the man. So acting on the man we have the tension T upward, his weight mg downward, the normal reaction N that's upwards as well. Let's assume the man's acceleration is A upward. Similarly for the box we have the tension T upward, the weight mg of the box downward, and finally the normal reaction N, which is the reaction force exerted by the man on the weighing machine. Now since the man and the box move together, their acceleration is same, so the box acceleration is A upward. Now we can apply Newton's second law. The sum of all forces equals mass times acceleration. Taking the upward direction as positive, we get these two equations. When the system is at rest, acceleration A is 0. Solving the two equations, we find N equals this expression. Since the weighing machine measures the mass, it will be the normal reaction divided by gravity and the reading will be 15 kg. For the second part, the man's actual weight corresponds to N equals mg, substituting which we get two equations and two unknowns A and T. We obtain T equals this expression and substituting the masses, we obtain T equals 1800 Newton. Thus, the man must pull the rope with a force of 1800 Newton for the weighing machine to show his actual weight.